In this lecture, we'll talk about thin lenses. Earlier, we had talked about mirrors or curved mirrors, right? Here we'll talk about thin lenses. So what is a lens? Lens is a transparent object with two refracting surfaces whose principal axis coincide. There are mainly two types of lenses. One is called converging lens or convex lens, and another one is called diverging lens or a concave lens. So we'll talk here about a few terminologies here. So we'll talk about a couple of terminology of focal length, optic axis, radius of curvature or radii of curvature. So let me talk about convex lens first. So it's made of two curved surfaces, refracting surfaces. So focal length, by focal length we mean if this is my optic axis is the axis passing through the center of curvatures of the two curves. So this is one curve, this is another curve, and whose principal axis coincide. So this is my principal axis common, and if I have parallel ray falling on it, so these are, let's say, my collimated beam, parallel beam falling on this convex lens, after passing through the lens they all tend to focus at one point, right? So they all tend to focus at one point, and this point is called focal point. This is normally denoted by capital F, and the length, the distance from the middle of the lens to that point is called focal length, and they're typically denoted by small f, similar to what we talked about curved meters. Right. Remember radius of curvature, there are two radii of curvature. Each face has a curvature. So, uh, this is the radius of curvature for one surface. This is the radii of curvature. We'll have another surface. All right. Okay. What happens if it is thin lens and it's a symmetric thin lens? Then if I have a rays coming from this side, from right hand side, then it will focus somewhere here, right? So it has two focal lengths, right? And if it's symmetric, that the focal lengths, we can say front focal length and back focal length, they are equal. Briefly, we can talk about the diverging lens. So similarly, we can talk about a diverging lens. So when a collimated beam falls on a diverging lens, the rays are diverges. That's what is named diverging lens. The lens bends away from the normal, and if you extrapolate or backwards, then these rays, outgoing rays, seems to be coming from a common point, and that common point is called a focal point. And then the distance from the lens of that focal point, from the middle of that will be called focal length of that lens. Obviously, in this case of the diverging lens, this beam, this focal point, this point is imaginary, whereas this focal point is real. So similar to when we're talking about curved mirror, we will talk here image of an extended object using a converging lens. So this is a converging lens. Let's say this is my extended object PQ of height h. So we will consider two rays coming out of, let's say, top of the object from point Q. This is a parallel to the principal axis. This is my principal axis. This is my back focal length. This is my front focal length of the lens. So parallel rays after passing through the lens will pass through the focal length or front focal length. So this is the incident ray, this is the outgoing ray, passes through that. Then there's the ray which passes through the center of the lens, and the center of the lens, this ray which passes the center of the lens goes undeviated. So it goes straight, continues. So incoming ray and outgoing ray, they do not deviate. And that's true for only for thin lens. Remember that the 2 points meet here, so that represents the Q prime. That's the image of Q, and so at that point you get an image P prime Q of height. Let's call it H prime. All right. Let's talk a little bit here. Then if you look at triangles PQO, PQO again, and P prime, Q prime, O, they are similar, right? And what it means is that means H over P, because that means this angle and this angle are alpha are same. So we can say H over P. P is my object distance. It must be equal to negative H prime. This is negative over I. That's my image distance. Or we can rearrange this. H prime over H is negative I over P. And then we similarly take triangles OAF2. This is my OAF2, and triangle P prime Q prime F2. So this triangle, and they are again similar. So we can say this height H, this is the same, this is parallel, so it's H over F, F is the focal length, is equal to negative H prime divided by this distance, and this distance happens to be I minus F, because this is my F, this is my image distance, so this distance is I minus F, right? And again, I arrange this one. This H prime over H is negative minus negative I minus F over F. So if I look at this, the right hand side or left hand side of this equation is H prime over H, and left hand side of this is nothing but H prime over H. So H prime over H, H prime over H. So these right hand side of these two must be equal. So that's what we are writing. Negative I minus F over F, negative I minus F over F must be equal to negative I over P, negative I over P, and each is equal to H prime over H, right? And then now rearranging that, so we divide this, so negative I over F, and negative becomes positive, and F over F is front, and is equal to negative I over P. So this implies, again, I'm dividing both sides by I, the image distance. So if I divide, then this becomes negative 1 over F plus you divide 1 over I is equal to negative 1 over P. So if I rearrange this one, then this comes out to equal to 1 over P plus 1 over I, and that is equal to 1 over F. So if you look at this equation, this is not the first time we are seeing it. This is same object image distance with respect to focal length is also seen in a converging mirror, right? And P is object distance, I is image distance, and F is the focal length of the lens. All right, so this is object image distance relationship for a converging lens. And of course, although we derived it for converging lens, but same relationship is valid for diverging lens also. So this is true for diverging lens also, of course, with the appropriate sign rules. Good. Just one more thing we can add here is the magnification of this lens. Magnification of this lens is given as negative I over P or equal to S H prime over H. Okay, good. So we got a the equation for magnification because of this lens. All right, great.